Tonight I'd like to welcome Professor Richard Easther, Head of the Physics Department at the University of Auckland, and he's spoken to us before. Some of you might be new and not know him. He always gives a really great talk of current topics of great interest in cosmology and astronomy. So Richard, thanks very much.
Hello. Thank you for inviting me along. I think the invitation came with a little bit of a challenge, in fact, because some work that I'd done with my group earlier this year was written up in the newspaper, and I got an email saying, "Would you like to come and give a talk on the stuff that you've just done?" And I'm thinking, it's kind of technical. I'm going to have to explain how everything fits together. I'll probably have to tell a whole story so that I can show where our little bit fits in. And then I thought about it for a while, and I thought, well, okay, challenge accepted. There's a saying that you don't understand, you don't fully understand what you've done as a scientist until you can explain it to someone who isn't a scientist. And for some things, that's more complicated than others. But I thought, okay, I'm gonna take this on. The other thing that I realized in the process of thinking about this is that the science of cosmology is actually, the modern cosmology is approaching its centennial. So 100 years ago, we had no idea that there were galaxies other than our own. The concept of an expanding universe had not been invented. And in the 10 years between 1920 and 1930, both the evidence that there were galaxies, the idea of the expanding universe, and in fact the first observational evidence for the expanding universe, all of those three things came together in a remarkably short period of time. And so the challenge for cosmology, or for people like me, is to look out into the sky. So here's the Milky Way as seen from Wellington and as uploaded to Wikipedia, which is very kind of someone. The challenge is to look out into the sky and to see something that people have been able to see and to think about it for as long as there have been people. Arguably, one of the things that makes human beings human is our ability to look upon the sky and to wonder what it is and how it got there and what the story of that is. And again, probably one of the defining things of human beings is that all of us create stories about what we see when we look up. The interesting thing about the story that we've been developing over 100 years is that it lacks, on the one hand, certainty. We don't know that we have all the answers. We're testing them. The story changes, has changed in my own lifetime and will change again, I think, in my children's lifetime. On the other hand, there's a growing sense that we're kind of getting to the bottom of things, that we're making sense of what we see. And so that combination of uncertainty, but also, the fact that we can feel change happening inside of our field means that as human beings, we're potentially living at a very special and unusual time. So my job as a cosmologist is to tell the story, as to how what we see when we look up in the sky came to be, how it's evolved as a function of time, and how we build up a narrative of the universe from the first instant into the distant and unknowable future. So here is a picture of the universe right after the Big Bang. This is obviously the boats are a kind of fanciful addition, but this, if you don't know it, this is a famous Japanese woodcut, The Great Wave by Hiroshige. But it shows at least whenever I have to give a talk about space-time foam, quantum gravity, and how when we get to small enough scales, space itself melts into this kind of quantum nonsense. I like to show this picture because it sort of gives me a sense of, even if we can't write down equations fully that describe quantum gravity, which we can't, you can look at this and you can sort of imagine what it feels like to think about it for any length of time. It turns out that one of the things we can calculate is that we would guess that if we zoom in, if we take a box of space and we cut it and we cut it and we cut it and we cut it, when we get down to about 10 to the minus 35th of a meter, that's about 10 trillionths of a trillionth of a trillionth. Is that 3 trillion? 10 trillionths of a trillionth of a trillionth of a meter. We get down to the point where we can't cut any further because space itself will dissolve into some sort of quantum mess. which we see here. So what that tells us is that's as small as space can be. So you might often be told that the Big Bang starts and everything is exactly 0 in size, but that's not strictly true. It's not 0 in size. It's 10 trillionths of a trillionth of a trillionth of a meter in size. And 0 and 10 trillionth of a trillionth of a trillionth, those are two very different numbers. Because if I take 0 and multiply it by a million, I still get 0. But if I take 10 trillionths of a trillionth of a trillionth and multiply it by 10, I get 100. Or if I multiply it by 1,000, and so I can, you can see how much expansion we need in order to take a little tiny blob of quantum space-time, which is as good as anybody else's guess as to what the universe might have looked like right after the Big Bang, and how much it has to grow until it gets to be as big as the universe is today. Okay, and so how big is the universe today? That's another question. So we look out into the sky. We know for reasons that I can talk about either maybe during the course of this talk, because I haven't given this talk before, so I don't know exactly how it's going to go, or certainly in question time at the end. We know that the universe is about 13.8 billion years old, which is a good number. We also know that it's about 40 billion light years from us to the edge of the visible universe. And so those of you that know that light travels at the speed of light and nothing's allowed to go faster, you might ask, well, how did that happen? And that's a fair question. And the answer is that light's been traveling towards us from the edge of the universe for 13.8 billion years, because that's as old as the universe is. But since that light leaves, it's also been stretched by the expansion of the universe. So the combination of those two things gives us a visible universe that's about 40 billion light years from us to the edge, or about 80 billion light years across. So the universe has grown from being a little patch of space-time, about a 10 trillionth of a trillionth of a, you're going to get sick of me saying that, a trillionth of a second, to being a patch about 80 billion light years from side to side. And so what that means is that we can go back to this, and we can say that that means that we have to have made the universe, or the universe has to have grown, by about 10 to the 60. In other words, 60 factors of 10 between being a little patch of quantum space-time that is so small that space doesn't really exist, to being as big as what we see when we look out into the sky today. There's about 60 factors of 10 between those two things. And I'm now going to play a horrible trick on you. How many people here knew that this was an audience participation thing? So like when you go to like a gig or something, and there's always one person who wants to stand up and participate, and there's everybody else, there's like someone who's going to hold up and say. So what we're going to have to do is we're going to have to clap our hands, and every time we clap our hands, the universe gets bigger by a factor of 10. So I've already done 1, and we need to get up to 20. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Each clap, universe has grown by a factor of 10. It's now big enough to hold one of these. In fact, not only all of one of these, it's now big enough just to hold the middle of one of these. So the nucleus of an atom is about 10 to the minus 15th of a meter, or 1,000th of a trillionth of a meter across. And a nucleus of an atom, after the universe has grown by 20 factors of 10, 10 to the 20 claps, is about as big as the center of an atom. So we're going to have to keep going. This is obviously no good. So let's try another 15 and see where that gets us. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Now the universe is big enough to hold this handsome fellow and also the guy standing in front of him. Okay, that's... I don't know, I'm sort of working cheesy tonight. So the universe is now a meter across after 35 claps. It's now as big as a human being. So the universe has grown. That's more than half of the total number of claps we're going to need to get ourselves to the edge of the universe. But let's make the universe a little bigger. Let's try another 7. Okay, so the universe is now tens of thousands of kilometers across, so big enough to hold the Earth after that much expansion. Let's try 4 more claps, and that will hold the inner planets. Another clap gets to the outer solar system. Another clap again, well beyond Pluto. So the whole solar system now fits into the universe that we've constructed. 3 claps will take us to the stars. 1,000 times bigger than the solar system, thereabouts. 2 claps, Milky Way galaxy. 2 more claps, nearby galaxy. 4, 2, 3, and now we're at the edge of the visible universe. See, cosmology is easier than it looks. I actually have a feeling that we may have only clapped 59 times, so let's do another one. It would be terrible to have a universe that didn't, get it home from the shop and it doesn't fit, it pinches across the shoulders. Okay, so how do we know? How do we know? And so the reason, as I said at the beginning, the thing that makes it different, or the thing that really is the kind of turning point for us, is the 1920s. So that's 100 years ago. So in my title, I said I'm going to try and do 100 years of cosmology in an hour. But that 100 years of cosmology describes the 13.8 billion years of evolution that the universe has undergone since the Big Bang. And so 100 years ago, this beast here was the state-of-the-art optical telescope. It's the Wilson 100-inch. Those of you who know about telescopes know that we measure telescopes across, not long. Short, fat telescope is as impressive or more impressive than a long, skinny one. So you look at that, that's like an 8-inch telescope, even though it's a nice big brass telescope, several meters long, a couple of meters long. This thing in the 1920s was the state-of-the-art telescope. It was the best telescope in the world. It was widely used by the person who gave his name, or who this object here was named after. So this is the Hubble Space Telescope. So this telescope was Edwin Hubble's workhorse. It's what he used to do most of his work. And here is a picture of Edwin Hubble. So Edwin Hubble turns up in the story twice. The first way that he turns up is that in the early 1920s, people for literally hundreds of years had been looking up into the sky with telescopes, and they'd been seeing, as well as stars and as well as planets, they'd been seeing little fuzzy blobs, little clouds that they called nebulae. Many of those nebulae are things that we now know live inside of the Milky Way galaxy. And the reason we know, and in fact the reason Hubble would have known that they lived inside of the Milky Way galaxy, is that when you look at these things, they're visibly involved with stars. You can see stars behind them. Sometimes you can see stars, in the case of some of these nebulae, being born inside of them. Some nebulae are the birthplace of stars, clouds of gas and dust. But there was also a bunch of nebulae that no one knew exactly what they were. There was one set of arguments to say that the nebulae, or some of these nebulae, were other galaxies like the Milky Way. There was another set of people who said, no, the Milky Way is basically all that there is. It's an island of billions of stars that lives in an otherwise empty and infinite universe. And so we've got the choice between these two perfectly reasonable ways for the universe to be. But by the end of the 1920s, we know that the answer is that there are other galaxies scattered through space, many of which are smaller than the Milky Way, but some of which are much bigger. That the Milky Way is a large galaxy, but the Milky Way itself is one of billions of galaxies scattered throughout the visible universe. So this band of light that we see across the sky, or in fact, conveniently, I think, across the back wall, it's actually another person I'm going to talk about is up on the wall there too, actually. What?
I think it was the same picture, just got blocked out.
So the Milky Way, we now know, is one of many such objects in the universe. The other two things, or the other thing we have to figure out, is not only that there are lots of galaxies in the universe, but that they're all moving. And it's not just enough to know that the universe is full of galaxies. The second thing we learn is that the universe is expanding. And so the two people who figured this out were these two people here on the right. We've got Alexander Friedman, a Russian meteorologist who one stage, I think, had the world record for climbing higher than anyone else in a balloon. So a bit of a daredevil, also a mathematician. The other one is Georgelemaitre, not on his way to a fancy dress party, but in fact a Jesuit priest, who was also a theoretical physicist working at university in Belgium through most of his career. Friedman died relatively young. Lemaitre certainly lived long enough for people to take his ideas very seriously indeed. Both of them, in Friedman's case in the early 1920s, in Lemaitre's case independently a few years later, both of these people took the equations describing space-time, the equations of general relativity written down by this guy, Albert Einstein, in 1915, and said, what would happen if I had a universe that was pretty much uniformly full of stuff? So it had no particularly special place, no center. It also had no particularly special direction. So wherever you looked in our universe looks different because we're sitting on the Earth. We know the difference between the ground and the sky. But if you take a random position in the universe, anywhere in intergalactic space, and assume that any random patch of the universe looks like any other random patch of the universe, you get a set of predictions. And one of those predictions is that you can have a universe full of galaxies, but you've got to go to a huge amount of trouble to make them stand still. They either want to expand, or alternatively, they would like to contract. Now, in some ways, it's easier to think of a small universe that somehow burst out of what Lemaitre called a cosmic egg, or a primeval egg, than it is to imagine a universe that starts out infinitely big and then collapses. So the assumption was that if you took Einstein seriously, if you dropped in this assumption that the universe was full of galaxies to the extent that there was nothing special about any one particular place in the universe on average, then what you got was this prediction that the universe would expand. Now, Hubble knew that he knew of Lemaitre's work, not necessarily of Friedman's, so he knew that this was a theoretical possibility, and it comes out of the way that Einstein tells us to think about space and time. So by the end of the 1920s, you have the knowledge that there are galaxies other than our own. You have the first evidence that those galaxies are moving away from us, which was found by Hubble at the end of the 1920s, this idea of redshift, that the galaxies, the more distant a galaxy is, the faster it moves away from this. And we tell that because the light in that galaxy has been shifted slightly to the red of where it would have been when it was emitted. And we get that because we've taken the ideas of this gentleman, Albert Einstein, seriously. And so we now have a different set of ideas about space and time. We've got evidence that there are galaxies other than our own, and we've also got evidence that the universe is expanding. So at that point, we have a universe that looks not unlike the one that we see when we look out into space today with our instruments. We also learn that these objects like this, so this is Centaurus A, it's a galaxy around 10 million light years from Earth, 10 or 15 million light years from Earth, one of the brighter galaxies in the sky. Also, if it's in Centaurus, it's going to be a good object in the southern sky. Galaxy like this, a sculpted galaxy, again, relatively easy telescopic object. This is again in the southern constellation, again about 10 million light years from Earth. These galaxies here, on the other hand, this is the Virgo cluster, or the center of the Virgo cluster, at a distance of about 50 million light years. So we can build our way out to the edge of the universe, but 50 million light years is a tiny fraction of that 40 billion that I mentioned before. So these things are still relatively in our stellar neighborhood. So one of the things that we get is that the universe has to have a story. It has a beginning, it gets to us, and over the time between the beginning, when the universe begins, there were no galaxies, there were no stars, there were no atoms. Everything has to be formed out of the stuff that's in the universe as it starts out. So one of the things we learn is that objects like the Milky Way have to be able to evolve as a function of time. They're not going to, the Milky Way or a big galaxy like the Milky Way doesn't just start out looking the way that it is today. It's going to age as the universe ages. And so one of the people who figured this out in detail is Beatrice Tinsley, a New Zealander, was born in England, grew up in New Zealand, got her PhD in the United States and died relatively young at the age of 40. Also, you can see there's two photos of Beatrice Tinsley. Fortunately, the one I got on the wall, one I got on this, is not the one that you guys have on the wall. But one of the first people to think in detail about the ways that galaxies age. And the galaxies age both because they collide with other galaxies, they have interactions, but also because the stars inside of them grow progressively older as successive generations of stars are born and die. And she was one of the first people to grapple seriously with what this meant for our understanding of galactic evolution. So I also promised that I was going to look into the future. And so one of the things that we are looking to do in the next couple of years is to use this instrument here. So this, as you can see, is an artist's mock-up, but it's mostly complete. It's been slowed up a little bit by COVID-19. This is the large synoptic survey telescope, recently renamed the Reuben Observatory after Vera Reuben. Again, pioneering astronomer, one of the people who figured out that the evidence for the existence of dark matter in the universe. So this, the job of this telescope will be to take a picture of the southern sky roughly every 4 days, and that picture will be complete out to a distance about halfway to the edge of the universe. So 30 or 40 years ago, getting a single image of an object that was at what we call a redshift of 1, about when the light left it when the universe was half the size that it is today, that could take you a night on a big telescope. This telescope is going to see out to a redshift of 1 in an exposure that takes about 15 seconds. So and it's going to do that for a giant patch of the sky, and then it's going to move, and it's going to do it again, do it again, do it again, keep that up all night, every night for 10 years, provided the Starlink satellites don't get too seriously in the way. Boo!
Is this in Chile?
It is in Chile. Another thing we're going to build to do this is the James Webb Space Telescope. This is what it looks like at the moment, or recently. It's folded up in a test chamber. This is what it will hopefully look like when it gets into space. Now currently slated for launch October 2021. It's a joke about most of these things that they tend to slip by about 6 months for every year. So if your telescope slips a year for every year, then you have a problem. If it slips only by 6 months every year, then sooner or later you'll get to a point when it's launched. So what was that? So hopefully this object will be on orbit soon. And the reason we're hoping it will be there, and the reason it will tell us things about galaxies, is it's particularly designed to see the light from some of the most distant galaxies in the universe. So light from the most distant galaxies, the universe has grown by a factor of 6 or 7 since it was emitted, which means that light has been shifted to the red by about a factor of 6 or 7. So you want a telescope that will be sensitive to the infrared, where it can see the light that's set off from the earliest galaxies in the universe, which is what this thing is designed to do. So over the next 10 years, our ability, the centennial of cosmology, 2 of the things that we're going to be using to make sense of what we see will be things that will give us a view of the universe that will be in many times better than what we are able to achieve today. Okay, so what we've got is we've got a view of the universe that grew by 60 claps. I'm not going to make you do it again. But where we are, how many people here have seen the movie Moana? Some. How many people? Okay, admit it. Come on, take your grandchildren. Nieces and nephews. Get a gig babysitting. There's no spoilers, but there's a key scene in the movie where Moana, the heroine, realizes that she has grown up on a single island, and she's been told by her people that this, in fact, is the only island in the world, and it's silly to think of going anywhere else. And so, of course, what she realizes is that, she's living in the Pacific, that her people have a history of navigation, and that she realizes that she can actually sail to the other islands that exist, and massively expands, her view of the world and her understanding of the world that she lives in. In our case, we are not going to find a fleet of intergalactic spacecraft cunningly stashed in a cave on an island. No spoilers here. But we are able to look out from the island of stars that we're living on and to see that the universe is in some sense a three-dimensional ocean that's full of islands. So that takes me one way of thinking about the Big Bang. Starts off as quantum foam, grows by 60 factors of 10, and eventually fits everything that we can see in the sky. There's another way to think about it, though, and that's in terms of time. So I said that the universe is 13.8 billion years old, but each of those factors of 10 takes a very different amount of time. So these are some of the most distant galaxies in the universe. This is an image that was taken by the Hubble Space Telescope, so-called Hubble Deep Field. Some of these galaxies potentially lit up first when the universe, or the first stars might have lit up when the universe was, say, 15 times smaller than it is today, or barely a single clap. Most of the galaxies in the universe, less than a factor of 10. So all of the evolution of galaxies in the universe, in terms of us being able to actually see them, much of that evolution has happened in the space of a single clap, if we're measuring. So we think those take an equal amount of time, but in fact, growing the universe by a factor of 10 has taken billions of years. If we look back to the time when the universe was 1,000 times smaller than today, that's about 380,000 years after the Big Bang. So at that point, we're 57 claps away from where we started, but only 380,000 years after the Big Bang. The image that I'm showing here is an image of the sky as seen in microwaves. And there's a couple of things that have happened, but what this does is this tells us the temperature of the sky. And so the thing that convinced scientists in the 1960s that the Big Bang was really what had happened was discovering that the sky was slightly warm. And what they discovered was that from every point in space, it looked as though the sky was glowing slightly because it wasn't exactly at absolute zero. It wasn't exactly at absolute zero, it was about 3 degrees above absolute zero, which means that that glows vaguely in the microwave band, about 160 gigahertz from memory. So somewhat shorter wavelength than 5G. I didn't say 5G, oh dear. So these people actually this is the telescope that was used by Penzias and Wilson. They made this discovery accidentally because they were trying to build an early communication satellite. They wanted to pick up very sensitive signals that were bounced off, literally a big balloon in space. The people who pick up sensitive radio signals from space are radio astronomers, and what they actually found was that the sky was glowing slightly with the aftermath of the Big Bang. This map is taken from a satellite, and what it does is it actually cheats a little bit because lots and lots of things have been subtracted from this map. This is a baby photo of the universe. It's as the universe looked about 380,000 years after the Big Bang. But what it actually does is it tells us how different the sky is in temperature from place to place. So this is the whole sky kind of unpinned, mounted on the wall. What they've done is it's like sitting on an ocean that's about 1 kilometre deep. There's a wind blowing, so there's a little bit of a chop. You're in a boat. The boat's kind of slopping up and down. What you notice is the way that the boat is slopping up and down. You don't notice how deep the water is. And so this is just the wave on top of the water. So the 3 degrees is the depth of the water. This is about 1/10,000th of the degree that changes from place to place. So the way that the picture's been drawn, it looks hugely lumpy and bumpy, but if you'd actually shown it properly, you'd see it as being almost perfectly smooth. So the universe, when it's 1,000 times smaller than it is today, is almost perfectly smooth. But the microwave background does two things. It firstly tells us that the early universe was hot, because as the universe expands, it cools down. If the universe is 3 degrees today, I go back by a factor of 10, like an inverse clap. I don't know how we do. How do we do a reverse clap? Like this, right? We go back by 3 factors of 10. The universe is now 1,000 times hotter than it is today, about 3,000 degrees. We keep on doing that. We go back to the starting point. The universe is millions, billions, and trillions of degrees right after the Big Bang, when it's really tiny. So it tells us that the universe is not only has been growing, it tells us that the universe is also cooling down. Again, in the future, over the coming decade, we're going to get better and better images of the Big Bang, of the microwave background than we have today. So if the universe is a few thousand degrees when it's 1,000 times smaller, 380,000 years after the Big Bang, imagine we go back now to a few minutes after the Big Bang. So this is 6 claps smaller now than the CMB, or than the microwave background. So again, 6 inverse claps, and we go back, I need to thread them. 3 minutes after the Big Bang, the universe is hot enough for nuclear reactions to take place. So the first atoms that are made in the universe, or the first nuclei that are made in the universe, are cooked a few minutes after the Big Bang, when the temperature of the universe is billions of degrees. In fact, hotter than the center of the sun. We go back a bit further, another 3 claps there or so, about 1/millionth of a second after the Big Bang. And even the protons and neutrons that sit at the center of atoms will melt at the temperatures we find then. We go back another 3 claps, a trillionth of a second after the Big Bang, and I think I've got my clap count right here. At that point, average interactions, typical interactions in the universe, are at the same energy as that we can cook up at the Large Hadron Collider. So in other words, earlier than that, whatever the laws of physics are, they're happening at energies that we cannot probe experimentally on Earth. So what I've just told you, if you were keeping count, is that once you're 15 claps back from where we are today, the laws of physics as we currently understand them break down. There are 45 claps left to take us all the way back to the first instant of the universe when it dissolves into quantum foam. And there are 15 claps that describe everything that we can describe with the physics that we know in the universe. But the 45 claps that we don't understand take place in about a trillionth of a second. So if you're thinking about the universe in terms of factors of 10, only a quarter of the universe of that expansion happens when we understand the rules of the game, when we know the laws of physics to some tolerable accuracy, and even then there are bits that we don't. But on the other hand, that first 45 factors of 10 in growth happens in about a trillionth of a second. So if you're a cosmologist like me, you spend a lot of time thinking about that first trillionth of a second. A lot of time. For a trillionth of a second, it's easily the most interesting trillionth of a second that happens in the universe. Right now, people are debating whether to build a bigger particle accelerator than the LHC, because you would like to be able to probe fundamental matter at higher energies than the LHC has been able to reach. If you're a cosmologist, you've been doing that since whenever, because most of the thinking that happens in early universe cosmology is happening at energy scales that the LHC cannot reach. So we have about 45 times 10, 45 times that tells us what happens when we don't understand the laws of physics. Every time we go back by a factor of 10, the temperature goes up by a factor of 10, roughly speaking. It's not strictly true, but it's true enough for a talk like this. No offense. In fact, it's reasonably true. And so what that tells us is that it tells us that when we push our way back into those early times, we're also carrying out particle physics experiments. So what cosmology has done is it's kind of gone to the kind of science casino, and it said, I would like to be able to explain the beginning of the universe. And then you think, well, that's fine, but I don't really understand the physics that would describe the beginning of the universe. I've got some numbers. I can give you that scale at which things become kind of quantum foamy, but I can't give you anything else. And I said, right, double or nothing. We'll understand the laws of physics at the highest possible energies, and we will understand the Big Bang. So far, we haven't been able to pull that off, but that's the point of cosmology in some sense, or one of the goals of cosmology is to understand that missing 45 factors of 10, that missing trillionth of a second at the beginning. There's two things that might happen in the beginning of the universe that would account for some of those 45 factors of 10. 30 factors of 10, and in fact it could be much more than 30 factors, but it's only the last 30 that we can see, would be described by something that we call inflation. And so what that does is it says maybe those first 30 claps happened super fast as the universe grew almost exponentially. And there's lots of reasons why we would like it to do that, to set things up, to provide the kind of universe that we see today, to provide the patterns that we see in the microwave background. And the reason we would like to do that is because babies can be messy. So how many people recognize this baby? That's Prince, what's his name, isn't it? Which one? Sorry? Prince somebody? Is it Prince William or is it Prince William's kid? I can't remember. George, that's right. So what this baby is, now anyone who's had any experience of babies, they have this baby in a white outfit. It is clean. So clearly this baby is what is technically known to the scientific community as fine-tuned. In other words, this baby, there's a platoon of nannies somewhere that have prepared this baby in a very special state. If you just pick up a random baby and you don't get chased down the street, the baby will not be as clean and shiny as this baby. And so universes are very much the same. If I take the sort of messy universe that I get out of that little patch of quantum foam, there's no guarantee that it will be smooth enough to provide me with a universe where the ripples in the microwave background are only different by 1 part in 10,000 from one place to another. But if I stretch the universe by some enormous amount, then all of the little bumps and ripples that were there at the beginning will almost all be completely erased away. And as I say, I need about 10 to the 30, a factor of about 10 to the 30 to do that. I also need, that leaves me over, and this is getting to me meeting the challenge about explaining what it was that I was doing that got into the newspaper. This leaves me about 15 factors of 10. And so our best guess for the energies that inflation happens at are that they are about 15 factors of 10 higher than the energies that we can reach at the Large Hadron Collider. So the universe has got to, inflation ends, the universe has to grow by maybe 15 factors of 10 to explain this missing bit in the middle. What happens there? Nobody knows. I don't know, you don't know, but what we do know is how it must come to an end. Because at the end of that 45 factors of 10, the universe has got to be hot enough to provide the kind of furnace, if you like, in which these nuclear reactions that take place in the first minutes after the Big Bang can happen. So if the universe doesn't get hot, you can't do this nuclear cooking. Most of the helium that exists in the universe, we think, is produced in the first couple of minutes after the Big Bang, and also little tiny fractions of things like lithium. So we can test quite accurately what goes on in these first minutes after the Big Bang, and so that gives us a constraint. Whatever it is that happens in that first trillionth of a second, it's got to end in a state that's going to allow the universe to roll forward in the way that we see it doing for us. But we do know how it must end, and this depends on physics that's beyond our current understanding. So one of the things that I've been doing is to think about what happens in the universe in that 15 factors of 10 after inflation ends and before the universe becomes ruled by physics that we understand. And that 15 factors of 10 is about a trillionth of a second. But if you think also in terms of kind of expansion time and not clock time, it's also that all of the galaxies that we see, all of the stars and galaxies, everything has formed in a time in which the universe has grown by only 3 factors of 10. So there's all kinds of stuff that can happen in this first trillionth of a second because all of the physics that happens, all of the particles, all of the interactions happen. Now every clock, if you like, ticks so much faster during this phase than it does today that you can actually form complex collapsed structures that would mimic the formation of galaxies today, but that would be all over and done with and then melt at the end of this first trillionth of a second. And so here's a rough picture. This is a completely this is a visualization of simulations that I've been doing with my students of physics that may in fact take place in this epoch at the University of Auckland. And the questions that we've been asking ourselves is how would we be able to work things out that happened in that first trillionth of a second between the end of inflation and the point at which physics as we know it comes into play? Would that leave any physics that we would be, or any fingerprints behind that we would be able to test with upcoming experiments? And I'm going to mention just 2 of them. One of them is that you can produce gravitational waves in this epoch. So not the kind that you've been hearing about recently where you have stars collide, they produce a burst of gravitational waves. It'd be something more like a bath of gravitational waves that would fill the universe. And also this epoch has to somehow provide the initial seeds that allow for the formation that eventually when stars and galaxies can form in our universe, it has to provide the seeds that will, the first initial bumps and lumps that will collapse to produce the galaxies that we see today. And so between those things, we're trying to look at the predictions for those things, get a handle on those things. We can test some of our ideas about the earliest parts of the universe. And that, I think I have managed to work the stuff that I was doing earlier this year with my students, challenge accepted from the Auckland Astronomical Society. I've also given you a lightning tour of the history of the universe, so less than an hour, 100 years of cosmology, 13.8 billion years of expansion, 60 claps. I'm not going to make you do it again. But that's where I want to end up. So thank you very much.
I'm sure that gave a bit of extra insight to people about what they've been reading about cosmology, and so a different way of thinking about it.
Yeah, it's a very experimental talk. I've been doing, like, I should have got ethics approval for this on you. but partly I was thinking, well, how do I talk about what we do in under an hour? So I guess we should ask for questions, right? And the questions are going to tell me. So there's not a test here or anything, but the questions are a test for me, but they're also a test of whether we actually landed this somehow.
I've got a question about simulation. Is that looking at quark-type level interactions or strings, or is it?
No, strings would be too small and quarks are much too big. Somewhere between the two. So the whole box is about 10 to the minus 20 meters across, I think, for the simulation. So tiny, but also much bigger than that messy quantum foam.
What's the difference between the edge of the universe and the edge of the visible universe, and why are we in the middle?
I thought I managed to swing that one under the rug. There's a big lump in the rug of cosmology. So the visible universe is the universe that we can see. So the reason we're in the visible universe is because we can see the same distance in every direction. So that's what we mean by the visible universe. Why the visible universe is as big as it is? Well, that's because the universe is as old as it is. On the other hand, the question of what lies beyond the visible universe, which is maybe what you were getting at, or I don't know, I'll take it that way, we don't know. So we believe, so 60 claps from the quantum foam will get you to the point where things were starting to look a little bit lumpy as you got right to the edge of space. So most likely, the universe has actually grown by more than 60 factors of 10. But it would be unreasonable, probably, to assume that the universe was absolutely no bigger than it needed to be, and we were right in the center of it. That would be kind of luck, right? But so most likely the universe is bigger than the patch that we can see, but at that point, it's a speculation about what seems and feels reasonable, rather than something that we can directly test experimentally. If we had better theories that we had verified in other ways that made predictions about the size of the universe, we may feel more comfortable making statements about it. It is true that inflation actually wants to last a lot longer than that 30 claps. If that's true, then the universe is much bigger than the patch that we can currently see.
With your claps model, at what number of claps does gravity separate out from the other forces and become attractive?
The first one. Yeah, so gravity begins as soon as space-time becomes classical. So as soon as you get bigger than that little quantum patch, or 1 or 2 claps, then the working assumption would be, and there's many other ways of doing cosmology that would involve different ways of starting it, but the working assumption would be as that gravity works as it does today, pretty much as soon as the expansion of the universe gets going.
So given the huge densities, why don't you get black holes forming?
Because the universe is smooth. So a black hole corresponds to having a whole lot of stuff in one place. In fact, technically, a black hole is what we call a vacuum solution. So in a black hole space-time, when you write it down, there is no matter anywhere. And the black hole itself is really like a kind of belly button where mass was in the universe and has kind of fallen. So as long as you're outside of the universe, outside of the black hole, you're in a vacuum. And so the black hole is this kind of dimple that's left over in space-time. It's been sort of knotted off. In the case of the universe, it's super dense everywhere, and so it's not going to collapse to form a black hole in a single place.
And once you get those fluctuations, presumably you would get primordial black holes.
If those fluctuations are too big, then you will get primordial black holes. We don't see primordial black holes, which tells us something about the kind of fluctuations that you can have in the early universe. And so even though you don't see them, the absence of those observationally then is one of the ways in which, not only one can, I have personally constrained the early universe by the fact that I don't want it to produce primordial black holes, because if it did, then I would have to explain why there weren't any primordial black holes today. Yeah. So you've just become a cosmologist. Congratulations.
Can you talk about the correlation between the variations in the cosmic background radiation and the distribution of matter in the observable universe, in so much as my poor understanding it relates to
that's a great question.
The curvature of space and if it's flat or not flat.
Okay, so there's two things going on here. When people talk about space being curved on large scales, they're tending to talk about this idea that a universe that goes to a maximum size and recollapses, if you draw a giant triangle in that universe, the sides add up to like more than 180 degrees, whereas the open one, less than 180 degrees, and the flat one is right on top of it. In a universe that has dark energy in it, which I didn't really talk about, will expand forever. We're being pushed in the direction of the flat case where triangles on big scales are 180 degrees. But the closed, so on large scales, we think we're living in a universe that is approximately flat. The lumps that you see in the microwave background are smaller, and so those have the same source, we think, as also the lumps that will, the early universe is slightly uneven, and the regions that just by chance are slightly denser than others, those are the regions where the first galaxies will happen. Or the most regions that are kind of just lumpy by chance, those regions pull more matter towards them because they've got a little bit more density, a little bit more gravity. Those regions are the regions that undergo gravitational collapse. All of those original lumps and bumps, we think, were actually, well, if inflation is true, then most likely those lumps and bumps were generated during that inflationary phase. So it wipes the universe completely smooth and then generates little lumps and bumps that then provide the seeds for galaxy formation and also the lumps and bumps we see in the microwave background. So both of those things, to the best of our knowledge, have the same origin.
And they do correlate on a distribution basis?
And when you look at the distributions from the way galaxies are distributed in space, and when you look at the lumps and bumps in the microwave background, they seem to be trying to tell you the same thing. So yes.
Richard, you spoke of 1 unit of redshift. Is there a relationship between the measurement of redshift and the distance that object is in terms of light years?
So yes, there is, and to do that, you need to know what we call Hubble's constant. And so, if we know that, for instance, an object has, been redshifted so that all of its light, the frequency has been decreased by a factor of 2, that blue goes to red goes to infrared. Then to figure out how far away that is, there's another number we need which tells us how fast the universe is expanding, which is this thing called Hubble's constant. And in fact, one of the weird things about the universe today, or the thing, if I was to put my finger on one thing that you might read about 2 or 3 years from now and say, big discovery in cosmology, would be that when we measure Hubble's constant from the microwave background, which we can do, we get a number of about 66. When we measure it the way that Hubble would have measured it, by measuring things that starts out from nearby things and working our way up to things that are further away, we get a number of about 74. And those two numbers have error bars on them, and those error bars have shrunk, but the numbers have not moved. And so we're now at the point where a few years ago it was kind of, it's a pain in the neck, but I'm sure we'll find out why they don't agree with each other, to actually maybe there's something interesting going on here. And it's, that joke about scientists, we don't say eureka and kind of go charging through the street saying how exciting things are. The sound of a scientific discovery is someone going, gee, that's kind of weird. And we're definitely at the gee, that's kind of weird stage on this one. But what it's trying to tell us, I don't know. Yeah, if I did know, I'd be home trying to figure it out. Sorry.
Got a question from the internet here.
Uh-huh.
It says, is there any idea as to what happened before the Big Bang?
Man, that rug is getting lumpier and lumpier. Yes and no, I think would be fair to say. There are so what we actually have a description of in general relativity, and this gets back to the great questions, by the way. This gets back to the question of when does gravity start working the way that we think it does. So immediately after one clap, you're basically doing standard gravity as far as we know. So general relativity doesn't describe the Big Bang itself. It only describes the immediate aftermath and then the subsequent 13.8 billion years and then on into the infinite future. So we don't have a detailed theory of what actually we mean by the Big Bang. There are versions of the Big Bang where you have a universe that collapses, that goes through some squishy quantum state and then bounces back as a new universe. And so that would correspond to these kind of cyclic universes. There's no particular reason to think that it has to do that. The main reason I think people like that is that it sort of puts away the problem of having to have a beginning. So you just stretch it out into the infinite past. And it's also possible to imagine universes that you have a kind of state that's sort of timeless and at an enormously high energy, and quantum mechanically you produce little batches of universe that, you know, little pieces of that quantum foam that then are then able to expand and to cool. That's as good as anybody else's guess. You can, in some cases, describe that kind of process mathematically. Again, something that I've been involved with as you know, I've written papers on this stuff. So you can do calculations about this, but I think it would be unfair to say, or would be unreasonable to say, that we had a detailed theory of what the Big Bang looked like. We have mathematical descriptions of things that would look like a Big Bang if you were living inside of them. That's not the same as saying we know how the Big Bang works. We don't. So yeah, it's a good question.
I have a question. We've got the cosmic microwave background as some kind of early probe of how the universe was, say 300,000 years after the Big Bang. There should be also like a background of neutrinos. So is there any possibility of ever detecting those, and would you learn anything from it?
You'd certainly learn. So the idea is in fact that you produce neutrino, or the universe has a population of electrons and anti-electrons that almost exactly collapse, annihilate with each other, and produce. In that process, you produce lots of neutrinos. That's a slightly loose way of saying it. But there is reason to think that there are about as many neutrinos in the universe as there are photons in the microwave background. Those would be very hard to detect. We can detect evidence for them in bulk, in terms of the way that structure in the universe grows. If you take the neutrinos out, the universe is slightly different. Being able to detect them individually, yeah, I think people have talked about it, but it would be a toughie. I mean, everything's possible if you build a big enough machine. But that would be a very big machine.
You talked about a trillion to the second.
Yeah.
And you then talked about how, from the point of view of what's inside the trillion to the second, time probably is not a trillion to the second. Is it, you know, from that time, things happen a lot faster? Are we talking from a point of view of the particles, it's billions of years? Or are we talking, you know, is it in some kind of exponential change so that there's time for all these things to happen? Or is it just a meaningless question? Because
no, it's a perfectly good question. So that the universe would double in size more rapidly compared to typical processes inside of the universe, in the early universe, than it would today. I think that's true. But as the universe expands, those timescales get further and further apart. So right at the end of inflation, the clock that's defined by a typical particle interaction and the time it takes the universe to double in size in simple models are about the same. But by the time you've gone 10 to the 15 times bigger, then lots and lots of stuff can happen in the time it takes for the universe to double in size just once. Yeah. So those two timescales separate. Yeah. Yes.
What does it feel to make a big discovery and be aware that only a few hundred people probably will understand it?
You know, if I well, partly that, you know, I don't know, but if I ever meet someone who's done that, I'll ask them and get them to tell you. I mean, you're probably right that there's probably, the community of people who work on early universe cosmology is small. I was joking once that we could probably all fit into a 777, certainly a A380. So, very important that it doesn't crash, right? At least if it does, everybody who wants to get a job in the field would be a suspect. I think, part of it is that, you as a scientist, you often produce things for your peers, but, one of the interesting things about cosmology is that if if someone knows that the universe is expanding, pretty much the first question they're going to want to ask is what was there before, which we've already had. The other question is the universe going to expand forever? The answer to that question appears to be yes, but that is an answer that was figured out in the lifetime, in not just in my lifetime, but in my professional lifetime since I got my PhD. And so, the fact that we are able to ask, questions that if you go to a new city back in the old days when we could still fly, before the sickness, it's like a dystopian novel or something, isn't it? Like you're getting in the cab from the airport to the hotel, and the cabbie says, why are you here? And you say, here for a conference. What are you kind of conference? Oh, I work on the Big Bang. oh wow, I heard about the Big Bang. Is the universe going to expand forever? You know, that's a question that your cab driver can ask, or a 5-year-old can ask, and those are questions that we're able to answer. So I think it's probably, you know, individuals, you know, like you kind of have pieces of things that you've worked out, but I think, and I will say that working in a field where you're grappling with questions that are that big is actually kind of cool. I really like it. Yeah, it's fun. I mean, it's. But I think if you spend too much time thinking about how fun it is, then you won't actually get anything done. And so occasionally, you know, you'll see someone who's clearly, like particularly someone maybe who's, you know, keen to be a student, and they'll say, you know, I really think this, you know, I'm so inspired by working out, you know, deep things about the meaning of the universe. You know, I too see myself as a successor of Galileo and Einstein and Newton. And you're thinking, that's great, but are you going to stay up all night figuring out why your computer code differs by a factor of 2 from the other computer code that these other people wrote? Because that's actually 99% of what doing cosmology feels like, is you know, trying to nail those details. And it's the feeling of it is actually trying to nail down detail as much as it is having deep and beautiful thoughts. It's only when you step back that you see the deep and beautiful thoughts.
Did you have a question?
In the way you described inflation, it sort of starts and then magically stops. But you know, there's this other view that inflation, in fact, is a continuing process, and the result of that is you get not one universe but multiverses. Well, I don't know why they like that idea very much, but where do you sit on that? And is your modelling?
The modelling that we're looking at primarily, at least the stuff that I talked about, is stuff that happens after the end of inflation, so in a particular universe. Multiverse, actually, that's something I've got another student who's working on that. I could have talked about that, but I didn't. In some ways, it's hard to end inflation globally. So you can have inflation ends in one place that feels like a big bang, keeps going someplace else, you know, generates other big bangs. In fact, that's not dissimilar to what I was talking about previously. Is you have a large patch of the universe that's kind of growing exponentially, and little pieces of it stop growing, and that feels like a big bang to someone who lives inside of it. I feel like that the multiverse, I feel like it may almost be unavoidable. If you have, if your mechanism for making the universe involves this very rapid period of exponential growth, it's very hard to bring that to a complete stop. It's easy for it to get carried away. If it gets carried away, then you've got a multiverse for any reasonable definition of the word. Yeah.
So I can ask another question. You talk about the temperatures and the energy levels being the same thing back in the small measure. How does that relate to the velocity of the particle and the speed of light? I mean, are these particles moving at beyond the speed of light?
No, everything moves at the speed of light or less. Mostly what it means is that these particles are behaving as if they are dominated by their kinetic energy. So they're what we call relativistic. In other words, they're particles that are either have no mass or are able to ignore the fact that they have mass and are moving at almost, but not quite not quite the speed of light. So in this limit where we're talking about something being very hot, we're saying basically all of its kinetic energy is kinetic energy. Almost none of its energy is its rest energy.
So the quantum foam is massless?
Oh, the quantum foam is weird stuff about gravity that we don't understand. So that's why I showed you the picture of the boats, because it was kind of trying to distract you from the fact that we don't. And it was worked right up until now. The boats, the clapping, all of those things are designed to so we don't have a working description of gravity and quantum mechanics. We don't have a working description of those two things together. And if we did, then we could say more concrete things about things like the beginning of the universe. But in terms of the stuff inside of it, you have very, very hot stuff that's behaving relativistically, not little rocks.
Provides a concrete limit.
How so?
The speed of light being the energy of a massive thing, or because it's massive.
Yeah, but as things get hotter and hotter, they just try to get closer and closer to it, and they're moving at closer and closer to the speed of light, and so it doesn't. The speed isn't the concrete limit. It's just the energy. The energy can become unlimited. Can become almost unlimitedly large, but the speed can stay close to the speed of light. not under the speed of light. Yeah.
There was a theory a few years ago where the claim was that the Big Bang was actually had a cause of collision between kind of parallel universes or branes.
Yes.
Is that
Yes.
still talked about? Or?
It's active. It's actively been worked on. I mean, the person who's most closely associated with this is a guy called Paul Steinhardt at Princeton. And then ironically, Paul was actually one of the people who also came up with some of the ideas behind inflation. So Paul has a dollar each way on this particular bet, I think. I think it's probably fair to say that it is something that's still talked about, but it's certainly talked about less than inflation. But there, I saw just the other day there was some more recent work out on trying to explain this. Yeah.
Yeah. So 15 claps. Atoms can form, so in the ionisation energy and the universe becomes transparent. But as you go further back, does the concept of particle lose all meaning? For instance, at clap 1 or 2, do photons exist?
Yes, they do, but in a kind of soupy mess. So the idea of having individual, distinct, and kind of unique particles that you could kind of follow around, I would want to say that would be after the first millionth of a second, maybe. Before that, everything is just soup.
Is it a quark, gluon soup?
For a while, yeah, but before that, who knows? So what you can have is you can have photons that are able to produce pairs of particles revert back into, and so these processes are able to continue pretty much indefinitely. And so you don't have kind of a distinct particle that you can follow for a period of time. Once you're a minute or seconds after the Big Bang, then you do have individual particles that would be persistent, potentially through to the present day.
So at what stage would your quarks be bound?
That's about a millionth of a second in. Yeah. Yeah.
Maybe we should leave it there. Is there any further internet questions, Steve?
No.
Cool. Okay, so thanks very much again, Richard.